Okay, well, good morning. Welcome to the, I think, 13th annual workshop. This is the 11th being held at Johns Hopkins University. And the tradition started 13 years ago at Rutgers University. And well, anyway, so this is today's program up to a certain point. I don't know, can you move it? Just the program is listed or in a hard copy over there on a chair, and some of you have gotten it. Well, I have some general remarks which I can start with. You're not required to read it. This year we're going to be working on 3 problems: parsing Arabic dialect, parsing a spoken structural event detection, and statistical machine translation by parsing. As you see, parsing is everywhere. And later on in this program, the team leaders and maybe the teams as well are going to tell you essentially the contents or the more detailed contents of these paragraphs. The teams were decided in a fall planning session. We have this session every year, more or less in early November, to which we invite proposals. As you see here, 9 proposals were reviewed, and then some of them, well, most of them were accepted, and those that were accepted, the representatives of those proposals were invited together with other experts, and in a 3-day meeting we discussed what was proposed and come up with compromises, etc., and the 3 teams are the result of it. Here is a list, and I don't want to go through it. Here's a list of what the proposals were originally about, and as I said, the 3 parsing teams came out of that. I should say that, of course, we will issue again a call for proposals for next year. We're going to issue it as usual by the end of this workshop, which ends in 6 weeks, and hopefully some of you will again put in proposals, or if you like the format of our workshop, maybe you will encourage your colleagues and friends to submit. This is the general activities that we have at the workshop. Tonight there's going to be an opening day picnic at 6 o'clock behind Clark Hall, and we'll show you where Clark Hall is. In general, on Wednesdays we have seminars by invited speakers. The speakers, I guess, are fixed and by now known, not to me, but some people will tell them. I mean, I know some of them, but I don't know what the dates are, etc. These speakers are what the team leaders and we kind of decided might be most useful to hear. On Wednesdays also, in the afternoon, there are team updates where people from the teams tell us what they came up with and what their progress is. On Thursdays, we have brown bag lunches with the undergraduates to see what track their progress, and we usually go out to dinner to some restaurant in Baltimore, and it says voluntary dinner. That means not everybody is everybody's invited, but not everybody is obligated to go. And finally, on Fridays we have an afternoon social. Wednesdays, I don't see it here, but we still have lunches, right? Yeah. We have lunches, common lunches on Wednesdays. Which will be in which room?
They'll be in the bottom lobby.
They will be in the bottom lobby. And some statistics on this year's participants. There are 34 participants, 17 senior researchers, 11 graduate students, and 6 undergraduate students. Some of you might know or not know that the undergraduate students were determined in a worldwide competition. and there was something like, I don't know, 12 finalists, from which the teams selected the 6 people they wanted to work with. And here is some statistic or listing of where our participants come from, and they are 22 males and 12 females. I think if you have any questions, I'll be glad to answer them. We'll switch. Are there any questions? I hope you will have an enjoyable 6 weeks. Usually, at least we flatter ourselves that they are enjoyable, and the next speaker is our Dean, Nick Jones, who's going to welcome you.
Thank you, Frank. It's a pleasure for me to be here this morning. I'm very relieved to notice, last time I was asked to do opening remarks, I was told, and the preliminary schedule showed 5 minutes, and then when I walked in, the schedule that was on the screen said 20. So it's kind of hard to walk in and have to come up with a 20-minute remarks. Fortunately, Fred was true to his word, and he offered me 5 and is giving me 5. I might say that I'm also happy this morning because some of you may be aware that, well, you can tell I'm from somewhere else. I'm actually from New Zealand originally, and I'm very pleased to report, in case you don't know, that the New Zealand All Blacks rugby team dispatched the British Isles Lions in 3 straight test matches, finishing on very early Saturday morning. So I'm riding high right now because of that. It really is a special pleasure to invite you all to this workshop. I came to Hopkins first in 1986, actually, as an assistant professor in civil engineering, and was here for 16 years and ended up actually for my last 3 years here from 1999 to 2002 as the chair of civil engineering. I then had a wonderful opportunity to go out to Urbana-Champaign, where I was head of the Department of Civil and Environmental Engineering at the University of Illinois. And I had a great couple of years there. I was really enjoying it. It was it is one of the best civil and environmental engineering programs in the country, if not the world. And I had a great time. But about a year ago, I had the opportunity to return to Hopkins as dean. And my comment at the time was that there were relatively few places that I would have left the position I had at Illinois for, but the opportunity to come back to the Whiting School as dean was one of those opportunities. A big part of the reason why I was attracted back, and of course there was a little energy barrier associated with this. You don't load your entire family in a moving truck and move them to the Midwest and then 2 years later move them back to the same place. But a big attractor for me was the nature of the work that is done here at Hopkins, and I had the privilege even in civil engineering to participate, is that we are strongly interdisciplinary. And this, I think, is one of Hopkins' greatest strengths. And in fact, in the Whiting School, arguably our departments and other organizational units that have been the most successful over time have been those that have focused on interdisciplinary research. Probably the most well-known example, of course, is our biomedical engineering department, which was formed as a rather unique at the time collaboration between engineering and medicine some 40 years ago. And we've actually done that one very well, and it's currently the top-ranked program in the country. But if you look throughout the school, you will find that there are interdisciplinary activities going on everywhere. And I think, from my perspective, CLSP is another one of those activities that really rises to this interdisciplinary challenge. A really unique combination of traditional disciplines combined in a very creative way, and once again, I think has led to the great success of this center. I think most of you don't need to be convinced of the importance of multidisciplinary research, because for those of you who are interested in this topic, you know that it is very necessary that a multi or even a transdisciplinary approach is taken to some of the problems and challenges that you face. My understanding is that this workshop is one of the highlights of CLSP's year. It's always a big success. It looks like it's shaping up to be a big success this year as well. I noticed the picnic on the lawn outside Clark Hall. I am hoping for no thunderstorms for you, because I guess you can come into Clark, but that's the one thing that can potentially put a damper on it. But it looks to me like it's shaping up to be a great meeting. I'd like to extend my welcome from the Whiting School of Engineering to you all to this workshop, to the Johns Hopkins campus and to Baltimore. I hope you have a terrific week. I'm sure you will. There are lots of things to do in and around the campus, and there are lots of things to do in Baltimore. If you haven't been to Baltimore before, it really is a terrific city. And I encourage you to take any opportunity you have to explore it. So again, Fred, thank you for the invitation to do a welcome. Welcome to you all to Hopkins, and I hope you have a terrific week.
Words from our sponsors. I see Jack Godfrey is getting up, so
just barely.
Sponsor is Jack Godfrey of the Department of Defense.
You'll be relieved to see I don't have any prepared remarks or slides. I just want to welcome everyone and thank Fred for putting all this together. I told Fred one of the things that I've, in addition to the interdisciplinary nature of the workshop, which we're always pleased to have. One thing I noticed about the workshop is that it's kind of DOD meets NSF in its methodology. That is, the questions that come to the workshop come from the community. They come up through proposals made by the people who really know their stuff, who understand the field, and they're guided, I hope not with a very heavy hand, by the government, which in the DOD mode is seeking technology, looking for solutions to problems. And the match between those two is the workshop. And you know, as the last 6 years when I've been involved as from the government side, I think it's been a really creative and productive match. And hope you'll continue that tradition. The other thing I really like about the workshop is that in spite of all the work that gets done, people seem to have a lot of fun. And I hope you'll do that. Work hard, have a lot of fun, and I'm sure we'll be happy with the results. Welcome.
I don't see Joe Olive. Joe Olive of DARPA.
Thank you for asking me to speak. I don't know how many of you know, we just started at DARPA. We're launching a program in language called Gale, and very aggressive program. Big part of it is machine translation, and our belief is that parsing is going to be one of the many things that will get us to the kind of targets that we're looking for. Technology is important enough for DARPA that it is one of the largest programs at DARPA, and we're hoping for great success in the program. And this is a very opportune time for this particular workshop, because there's a good chance that things that come out of here will be a great help to our program. Thank you.
And next is Sanchi Kurampur, who's going to tell you about the activities that went on the previous 2 weeks.
Actually, this is called pre-workshop activities,
Or maybe
version
even before that.
2005, and I'll tell you basically how we got here. Right, so, like, you know, everybody thinks of this as a summer workshop, but if you're at CLSP and you're involved with organizing it, it actually runs all year round. And essentially it starts, well, you're over here right now and this workshop is going to get over, but right when it gets over, it comes a call for proposals for next year, which Fred mentioned. So that starts in September. We start soliciting proposals, even as we are submitting the final reports for this year's workshop. The deadlines are typically in October. And in November, we have a peer review meeting. This is what Jack was telling you about. This is NSF meets DARPA kind of thing. So the proposals come from the community, but they're reviewed in a peer review fashion. And then we select the team leaders at that time. So sort of the seeds of the proposals are sown at that time, the teams. And then we start soliciting money from DARPA and other agencies, saying these are the projects we want to do, give us more money. We have a contract in place from NSF, but it always gets augmented by other things. By January, hopefully, when people come back from Christmas, we have the senior members of the team finalized. And we usually give them first dibs on which grad students they want. And typically, if you know professors, they're useless without their grad students. So we let them bring their own grad students with them. And then in the meantime, right around December, before everybody goes home for Christmas, we send out this really big, wide, cast this big, wide net for undergraduates. And we start telling people how great it is and they should apply. And that deadline is typically somewhere in February. And then in March, we pick the best of the best. And in fact, it's so hard to turn some of these people down because we have only so many slots. But they're really fantastic students, and so that's always a good thing to have. And then, of course, by this time, the teams are finalized and the teams meet. And this is something that we insist on, that every team meet face-to-face in person as a group at least twice before the summer. And so they meet once sometime around March 8th. This is, by the way, a tentative schedule, and things slide a month back and forth a little bit, except for this red part. And then, of course, every team needs new data in this field. You know, things have become very statistical and empirical, and you have to collect data, annotate something, have people diagram sentences, and so on. And we send out contracts for that to NDC or agency for that. And then finally, come June, we get our workshop lab, which is down here in Schaefer this year, and we essentially uproot all our computers from our lab, bring them in there, set it up, and what used to be a classroom with blackboards now looks like a computer lab with 40-odd computer terminals. And then comes the summer. And then there is the summer school, or the NAACL, NSF, JHU summer school, I'll tell you about that. Then there's the main workshop, and then the cycle repeats itself. Right? So this is really what we do. So how did it go this year? Well, the call for proposals was issued in July. Like I said, it keeps getting earlier and earlier every year, because what we do is we try to hit the summer conferences to let people know that they could propose something for next year. And so that's when it starts. We typically announce it at various conferences, dozens of mailing lists, and then we contact our friends in the government and say, look, if you want something interesting to happen, tell the people who do good things in your view to send us a proposal. But the proposals come from the researchers themselves. This year we got 10 or 11 proposals, and we essentially just vet them very, very preliminarily for things which are completely out of the scope of the workshop. So I think the one we did not take this year had to do with doing a theoretical study of grammars and sitting and discussing grammatical formalisms to see, and it was more of a linguistics proposal than a cross-disciplinary. But other than that, most of the viable ones come through, and then we have a 2-day review panel. This year it was on November 12th and 14th. And essentially we bring in the authors, so this is where it's a little bit from NSF, but the authors come there to defend their proposals. We bring in peers, other experts, the government program managers, and there's a discussion, a lot of debate. And by the way, the proposals get seriously revised during this discussion to address any concerns that people might have. And then people vote. And Jason Eisner, my colleague, has set up this very nice single transferable voting scheme where people can vote without any biases and without any agendas. And basically the vote comes out about right. And those of you here in the summer, Jason can show them his program. It's so simple, even I could use it. And anyway, and at the end this year we selected 4 proposals, but we were looking for funding, got enough only for 3, so we now have 3 teams in the summer. Right, so what were the proposals considered? Well, there were a whole number of them. Fred showed this slide earlier. I just want to put this up again to tell you that the proposals sort of come from all over the place. We had some from Sheffield and East Anglia in the UK. We had most of the others from around the US. And then these were the titles, some in speech, some in translation, some in other forms of language processing, and so on. And these were the people who were there. So this is again something that Jack mentioned. So this peer review panel, it's not run like DARPA where somebody tells you what to do, because if you notice the government participants only form a small fraction of the people there. Most of the people there are so academics who either propose or who are reviewing the proposals or discussing it with others, and then there's a small number of us who are essentially acting as referees and trying to make sure the discussion moves along. And we try to get a good balance of academia and industry. This year is a little odd in the sense that this fraction is smaller. Usually we've had many more people from industry in the past. So this is typically the distribution of people who show up. And what happened this year is we have 3 teams. The first team is working on parsing spoken Arabic, and it has 6 senior members, 2 grad students, and 2 undergrads, and it's led by Owen Rambo. And those of you who haven't figured out the colored code, blue is boys and pink is girls. Red is team leader. This is the second team on parsing and spoken structural event detection. This is to find linguistic structure in speech and to use it to recognize speech better. This is a team led by Mary Harper from Purdue. Again, it has 6 senior members and 3 graduate students and 2 undergraduates. And finally, we have a team on statistical machine translation by parsing. This is a team that seems to be creating a lot of excitement in the community in general, because there's a raging debate on where NT is going to go next. So hopefully they'll give us all the answers by the end of summer. And this team was led, well, actually this team said we don't have any leader, we are all co-leaders, but like, I'm a person of habit. I have to have one person that I can blame when something goes wrong, and that person is Dan Malam. There are lots of grad students in this team, a couple from Hong Kong, we have one of our own, and then there are 2 undergrads, Andrea Burbank and Pamela Fox. So these are the teams, and all of you are here. So hopefully over the course of the day, those of you who don't know each other will introduce yourself to each other, and because you're going to stay together for 6 weeks anyway, might as well get to know who your friends are. Okay, so how did this whole thing start 2 weeks ago? Well, we started off 2 weeks ago with the summer school. This is a 2-week tutorial on many aspects of human language technology. And actually, to tell you the truth, we started this in '98 because we decided we'll have undergraduates in the program. And sort of after deciding to have them, we realized that, well, they probably don't know anything about speech and language because they're rising seniors. So we started off thinking, okay, we'll organize a few tutorials, give them an introduction. Hopefully they'll all get excited and come to grad school, and it'll be great to have these good students amongst us. And this whole program picked up, and people from DoD started sending in their new employees saying there's a quick way to learn what's going on in the field. And then NAACL, which is the North American chapter of the Association of Computational Linguistics, also thought this was a great program. They started sending a dozen odd students to us. And so by now we have more than 30 students in this program every summer. It lasts 2 weeks, and a typical program essentially looks something like this. So every morning there are 2 lectures, so the blue lines are lectures, and every afternoon I don't know what color to call it, is a lab. And every day has a theme of sorts. So the first day, on June 27th, we talked about automatic speech recognition. On 28th, we talked about spoken dialogue systems, and Alison Powell actually gave them a demo of a full-fledged information access system, but this is one of the TIDES portals, if you know what that is. And then we talked about statistical machine translation. June 30th was Jeff Bill's day, and from morning to evening he gave lectures and a lab on machine translation, and then we had machine learning, I'm sorry. And then on July 5th we had introduction to information retrieval. This is the web searching and the Google stuff that you all know about. And then the last 3 days are dedicated to the 3 teams, trying to bring everybody, all the students up to speed on what they're doing in the summer, and those are again the 3 teams that we talked about. Right? So this is where we are now. So we've done the 2 weeks of the summer school. We're getting ready for the 6 weeks of heavy lifting. But again, hopefully now you have a sense that we just didn't start now. We started way back in November, and these things have been building up. So what's in store for the next 6 weeks? Lots of things, actually. So the calendar looks pretty full. I haven't even actually, I've written more stuff, but it sort of falls in behind this and you don't see it. So there's something going on almost every day. As Fred mentioned, we have plenary speakers every Wednesday, and we've lined up all of them already. So we have Eugene Cherniak coming this Wednesday, Matthew Stone from Rutgers next Wednesday, Dan Klein from Berkeley the Wednesday after that. In fact, we had 2 speakers, so we have a second one that afternoon, John McDonough from Karlsruhe, Elaine Chi from USC, and Stefan Dressler, I think now from Xerox. So this is what's in store. Every Thursday, like Fred said, we meet the undergraduates just to keep track of what they're doing and that they're making progress and not out. On Thursdays in the evening, there's a social, there's a group dinner. Friday is important day. 4 in the afternoon, you get to eat ice cream, and those of you who are getting a per diem from us get their per diem checks. But of course, the important date to remember for those of you who are visiting are August 17 and 18. So these are the last 2 days of the workshop, where each team gets pretty much half a day to tell their story, very detailed. And this is an event for which you should expect visitors. I already know people from CMU and other places who said that they would send somebody here, a couple of people, to listen to these last 2 days to see what's going on. Because usually all the effort that you've put in receives a lot of attention in the community. So you should be prepared to, those of you who are in the workshop, be prepared to tell the story on those days. Those who are coming in from outside, be prepared to hear a good story on those days. And more importantly, invite your friends. Others in your university who are curious to know what you're doing, or others in your field, let them know that those are the 2 days where they should come, or even the other days. Well, if possible, just tell us a little bit in advance so that we can plan for food. So in case the MT group has roaring success and 80 people are going to land up on us on August 17, we'd like to know. So, well, that's because we provide food. And again, mark August 17, 18 on your calendars. Those are the final days of the workshop. Right. Thank you very much. Any other questions?
So now we're going to have presentations from the team leaders. I think the Arabic team comes first. On Rambo.
Okay, I'll be talking about the Arabic parsing team. This is our team. Sanjeev already showed these names. I just want to also draw your attention to our list of external participants who will be here for various periods of time at various times over the summer, and will also be helping us from wherever they are otherwise. I want to start out by saying why we should be interested in parsing Arabic dialects at all. The situation in the Arabic-speaking world is as following. All throughout the Arabic-speaking world, there is one common language called Modern Standard Arabic, which is used in written communications and formal spoken situations. So here's a sentence that means Nizar did not buy the new table in MSA. Then in addition, there are a large number of dialects, in fact a continuum of dialects. So here, for instance, I don't know if you can see it, this is Egyptian, right? So Egypt just kind of turned light blue there. This is the way you would say the same thing in Egypt, and without going into detail, I just want to draw attention to one change here that's highlighted. The negation in MSA is a separate word, and it's sentence initial followed by the verb. In Egyptian, the negation becomes a circumfix clitic around the verb, which is now following the subject. Now, if we look at other dialects such as Levantine here and Moroccan here, we'll see that the word order is the same, but certain lexical choices are different. What affects dialect usage? It's mainly geography, but note that it's a continuum. It's not the fact that there are, say, 5 distinct dialects. There may be 5 dialects groups, but that's just a way of categorizing them. In addition to geography, we also have an important distinction between city and village dwellers, between Bedouins and sedentary people, and then other factors, other sociolinguistic factors such as religion, gender, and so on can affect dialect use as well. So what we have is a multidimensional continuum of dialects. Here are examples of lexical variation. I don't want to go into them in detail. Here is verb morphology, the point about the circumfix negation. I don't want to go into that in detail. Because this is about parsing, I just want to talk about the syntactic difference, namely the basic issue of word order, subject-verb object or verb-subject-object. Both orders are possible in Modern Standard Arabic and in all the dialects. What is different is, first of all, that the distribution is different. So that in MSA, the VSO order is much more common, whereas in the dialects, the VSO order is highly marked and the SVO order is the standard order. Secondly, we do find a syntactic difference, namely the agreement facts are different, so that in Standard Arabic, in MSA, the verb shows different types of agreement depending on whether we have VSO or SVO order. This is not the case in the dialects where the agreement is the same, no matter what the word order is. Here's some other syntactic differences just to give you a flavor. To express a possessive in the standard dialect, we have a construction like the English apostrophe S genitive, where we just line up the 2 nouns one after the other. In MSA, we have the head noun first and then the possessor. In addition, the dialects have a construction that's like the English of construction, so we can say John's book or the book of John. In the dialects, the book of John type construction is much more common, and in fact it follows the English word order as well. It doesn't follow, it has the English word order as well. And note that the word used for of, the particle that creates a possessive construction, differs widely among the dialects. And another kind of difference we find are demonstrative. So to say this man in MSA, we actually say this the man. The word order is different in Egyptian, for example, where the demonstrative pronoun follows the head noun rather than precedes it. And one more important point about the use of dialects and Standard Arabic in the Arabic world, we find code switching. What does this mean? That in certain contexts where speakers know they are supposed to be speaking Standard Arabic, they often will nonetheless revert to their dialect. So here, Nizar took a transcript from Al Jazeera talk show, as they are posted on their website, and coded in black what is Standard Arabic and in red what is Levantine. The formatting is a bit bizarre here. It's just normal Arabic text, actually. And you see that there is just switching back and forth between words. And there are examples within a word, too, where a word is formed from morphemes from different dialects. So why should we study Arabic dialects? So first of all, there are no native speakers of MSA. No one speaks the standard dialect at home growing up. This fact, by the way, means that for some linguists, MSA is actually not a natural language, strictly speaking. Almost no native speakers of Arabic, meaning of the dialects, are actually able to sustain continuous spontaneous production of MSA speech. So in those contexts, like the talk show I just mentioned, where they're supposed to speak MSA, they actually don't succeed, as was demonstrated by this coding. So where you do find MSA speech is in scripted situations, broadcast news where the broadcaster is reading, or read speeches, political speeches that are read, and so on. Now, these facts, of course, affect all spoken genres which are not fully scripted, such as conversational telephone speech, but also talk shows, interviews on broadcast news, and so on. And in addition, we see recently with the growth of new electronic media that the dialects are starting to be used in written form more frequently by a larger group of people in things such as news groups and blogs and so on. Now let me give a very quick overview of existing computational resources for the dialects. I don't want to just rattle down a long list of things that exist and so on, but it's important to understand what exists and what doesn't in order for us to motivate our approach. First of all, we have transcribed speech corpora. We will be working on the Levantine corpus transcribed by the LDC. We also have Egyptian from a previous LDC effort, and there is also Iraqi and Gulf and perhaps others from various sources. Because this is hand transcribed, these of course are fairly small corpora by the standards of today's unannotated corpora. There's very little other unannotated text in the dialects. This is because when people write, they're supposed to write in Standard Arabic, not in the dialects. So what we can find online are the blogs and news groups that are already mentioned. This is an area that has not yet been explored in great detail. On paper, we can find some things such as novels, plays, soap opera scripts, and so on, which all have many different issues, starting with the dialect distribution, the orthography, the availability, and so on and so forth. Then we have some tree banks, which are quite small. In fact, so far we only have the Levantine tree bank, which is currently being created by the LDC after Johns Hopkins kindly leaned on them to do so. It's being created for this workshop initially, and we will be using this tree bank only for evaluation. Our approach does not assume that we have a tree bank for the dialect, but of course we need to know how well we're doing. So that's why we need this tree bank. I should mention also that originally we were expecting a tree bank to be based on the Egyptian corpus, but LDC preferred to work on the Levantine because it had been created more recently. The Levantine transcripts have been created more recently at the LDC. So that we had to retool from Egyptian to Levantine at the last moment. So lexicons, what do we have? For Egyptian, we have some resources associated with the LDC transcription that was done in the 90s, such as a monolingual lexicon. We had created under a separate NSF program an Egyptian MSA bilingual dictionary, and now because we had to switch to Levantine, we're in the process of creating a Levantine MSA dictionary. This would be about, we're hoping for about 2,000 lemmas in this dictionary. In addition, there are various word lists for dialects, such as at Castle, at Maryland, on the web, and various published sources. By published, I mean on paper. In terms of morphological resources, again, for Egyptian, we have some things that come out of the previous LDC effort. At LDC right now for Levantine, Tim Buckwalter is adapting his morphological analyzer for MSA to Levantine. We're not sure when that will become available. And at Columbi, we also have a morphology project which is oriented towards the dialects, but we do not currently have a Levantine analyzer. And I want to contrast this situation to MSA, where we have, first of all, huge unannotated corpora, because there's lots of published online MSA text. We have a tree bank which is continuing to grow, and I think the goal is 800,000 words of tree bank text. We have lexicons both online and on paper, monolingual, bilingual, MSA English, MSA French, and so on. We have morphological analyzers, taggers, chunkers, parsers, machine translation system, ASR system. We have the whole thing. And most of these things we do not have for the dialects. Let me tell you about the proposed approaches. So this is our basic situation. We have the dialect, and what we have here is a small language model based on the transcription done. And then we have this goal of having an input sentence, and we want some syntactic analysis. And I'm giving a dependency analysis, but that's not crucial here. In MSA, we have tree bank, we have a parser, we have larger language models, and we have other stuff as well. So the question is, and the parser may be derived from the tree bank, or typically is, and the question is, how do we get that step there? And what informs our approaches is, first of all, the fact that there are many different dialects. We do not want to solve this problem for Levantine. Even though I'm talking about Levantine a lot, we are using Levantine as an example. The solution we're aiming for is not a Levantine parser. It's an Arabic dialects parser that we instantiate for Levantine. Well, they're spoken to their few written resources. We don't want to assume that we can have access to 20 million unannotated words. We're not going to assume that we have access to a tree bank. And we want to be able to account for code switching, though this will actually be outside the scope of this summer workshop. And that's a conclusion that I already said. We're not going to assume large resources. What do we do? Well, the key idea, of course, is the fact that we have all these resources for modern standard Arabic, and while there are differences between MSA and the dialects, they are perhaps not as big as the differences between, say, English and Chinese. So we should make use of that. We're going to exploit the similarity between MSA and dialects, and furthermore, we're going to exploit our knowledge about these dialects. We're not going to, if we have explicit linguistic knowledge about how the dialect differs from MSA, we will use that rather than expect it to learn these facts from corpora, because these corpora don't exist from which we could learn it. And we have three approaches. Here's the first approach, which we call dialect sentence transduction. We start out with our sentence over there in the dialect, and we move it over into MSA using sort of a rough and dirty translation where we translate each word separately into a large number of possible translations over here, perhaps do some possible reorderings. We get a big lattice of possible MSA strings, and then we use our huge MSA language model in order to choose one MSA string. And if you look carefully, you'll see that the word order has changed, for instance, from SVO to VSO, and the agreement facts have changed. Now we just use an existing MSA parser, parse the sentence, get an MSA syntactic analysis, and then we map this MSA syntactic analysis back to the dialect. Then we get our dialect analysis. And notice that actually nothing happens in the dialect once we've transduced out of it. Everything happens like the MSA, the resource-rich side. In the solutions 2 and 3 are similar. In solution 2, we transduce the entire tree bank. So we start out with the tree bank that we have that's growing, and we just move it over into the dialect. Again, we will do this using heuristics and overgeneration. And then we'll use the existing small language model over there to constrain the solutions we propose at the dialect side. We then use the tree bank in the usual manner to derive a parser. And it is this parser then that we can use to parse the dialect sentence. So here you see we actually just use the MSA tree bank and then move over to the dialect as quickly as possible. In the proposed solution 3, we do an MSA grammar transduction, essentially the same thing, but instead of transducing the tree bank, we first derive the grammar from the tree bank. We then move the grammar over to the dialect using our explicit knowledge of the linguistic differences, and we then use our and in that context, we may also use a small language model in order to limit the lexical transduction. We then use this grammar to build a parser and parse a sentence. And note that, of course, this is not just a grammar, it is a grammar with some sort of probabilistic models, so that this parser is also a stochastic parser. And what do we use for the grammar? We will be using a tree adjoining grammar and, in fact, a probabilistic tree adjoining grammar. Let me summarize what we have done so far. We had, as Fred mentioned, we had two, or Sanjeev mentioned, we had 2 meetings in the spring, which were very productive. Unfortunately, some of us were not quite as productive as we had hoped because of Gale and all sorts of requirements from that. So what have we done? For common accomplishments that are required, that provide underlying resources and algorithms for all 3 approaches are as follows. First of all, we did baselining using MSA parsers on Levantine. This is done and ongoing. Then we have the seed MSA Levantine dictionary that I mentioned. We've just started doing that actually. That's being done by hand by a lexicographer at Columbia. We have done a small project to find Levantine text automatically on the web by doing web crawling, searching for key Levantine words. We have estimated language models for MSA and for Levantine. The MSA is done, the Levantine is ongoing. And we have a detailed proposal for how to estimate lexical translation probabilities without a parallel corpus. This is needed in order to do the transductions of sentences from dialects into MSA, or to transduce a tree bank or the lexicalized grammar from MSA into the dialect. For the dialect to MSA sentence transduction, we have the sentence transduction transducer implemented. It runs on Egyptian because we didn't have the Levantine resources yet. And we are currently adapting that for the Levantine resources. And we're currently also working on the back mapper for the trees that are generated in MSA to make them look like dialect. For the 2 approaches involving the MSA to dialect direction then, we have extracted a grammar from the MSA tree bank, so some more work is needed there. We have implemented a tree transformation rule formalism and started populating that with rules for the MSA to Levantine. This will be used both for transducing the tree bank and for transducing the grammar. So the same tool will handle both approaches there. We have developed a detailed proposal based on synchronous grammar, where the synchronous grammar can either be explicit or hidden, depending on whether we're transducing a grammar or a tree bank. Again, the key thing is that it does not rely on the existence of a parallel corpus, because we don't have one. And we have developed a model for estimating parameters called tree bank transfer, where, again, we don't require a parallel corpus. Now, the work plan is as follows. We will implement all 3 proposals by the end of week 2, we hope actually earlier, and at that point we will determine how to proceed given the results of the 3 approaches. It might be the case that we will abandon one at that point and just continue with 2. So here's a summary. The key point is that we have a continuum of Arabic dialects. People who communicate spontaneously in Arabic do not do so in MSA, but in the dialects. That's why we want to study them. There has been no computational or almost no computational work in dialects. There are almost no resources, and we do not want ad hoc solutions for one particular dialect that might be at the center of attention today. And our general approach is to exploit knowledge that we have of MSA and the dialects. Thank you.
How we're running on time, but we certainly have a section of questions.
We have 10 minutes for questions.
And we're running on time?
Yes.
Right, okay. So,
Yes.
We have dialogue going with Mohammed Mamouri and so forth at LDC about the constellation of problems associated with transcription of spoken Arabic. Do you have good lines of communication with them so that any implications of work done here?
Yes, yes. They have sent us an initial version of their Levantine tree bank, which we will be commenting on, giving them comments so that they can continue the work. They were consulting with Nizar, who's a native speaker of Palestinian, on their orthography for the Levantine. On orthography and transcription issues, there are many different opinions. but we understand the choices they've made and we find them perfectly fine. So
Because in general, what we were aiming at was not some magic cross-dialect single orthography, but some principles, some guidelines, set of principles that would make the transcription of dialects wherever possible MSA inspired or MSA compatible, and so I'd appreciate if two communities stay together on that.
yeah, no, we definitely work with them quite closely. For a time we had a weekly teleconference call with them,
Great.
and I think we'll start this again while we're here, just to give them feedback. Yeah. We think generally the work they're doing is very good. And,
Well, it benefits everybody because
Yes.
then the resources become
Yep.
more fungible across the communities.
exactly.
Any other? Oh,
In the Arabic tree bank that they already have, I mean, did by any chance some dialectal Arabic sentences slip in, or were they very careful in making sure they?
I think there isn't much dialect in there, right? So because it's edited, I mean, it's newspaper text, it's edited, people trained to write MSA. It just wouldn't happen. Yeah. Yes?
Brian.
So, in the diagrams, you're basically producing parses of the dialectal Arabic, and I'm wondering if you have any intention to take, say, large, well, I guess they're all small, but small transcribed data from the dialects, extract the parses, and then maybe do an iteration of EM or something like that to sort of firm up the...
Yes, yes. We have one proposal using Gibbs sampling to exploit this small, I mean, actually this point isn't small language model, but simply small unannotated corpus, to exploit that in estimating the parameters for this parser. Yes. And the interesting empirical question will be, given that it's such a small corpus, how well can we do?
Are you going to have eventually, or maybe not you, but your successors, a direct grammar for the dialect, rather than...
Yes, I mean, this is supposed to be here a dialect grammar that just stands on its own. I mean, once
Okay, and the parser
Yeah.
will be then from that grammar,
Yep.
and it's going to be direct, and
Yep, yeah.
and this connection...
Is lost, yeah. I mean, we could have gotten this from some other source at this point. The connection is lost.
David?
Oh, and can you go back to solution number 1?
Sure.
Are you going to save sentence pairs of MSA and dialect for potential MT training so we can do translation from dialect to MSA and back?
Well, I mean, it seems to me, well, yes, but it seems to me that, I mean, we're essentially doing MT here in a very rough and ready way. And our hope is that the quality of the MT will not, even if the quality of the MT will not be very good, the parsing will still end up choosing a structure that, when induced back, will be good enough. However, it's not clear that this system will give you sentence pairs of good quality dialect MSA.
Although presumably you could use parse correspondence to actually filter your lattice more effectively than just an LM.
Well, but where would we get the parse correspondence from, if not from the data we create ourselves?
Well, the next iteration.
Yes, but it's not clear to me where we get the increase in quality there. Because, I mean, there is no parallel corpus, even a seed corpus. That does not exist at all. So,
Using multiple techniques, the synthesis of them
perhaps, yep.
potentially.
Yeah, okay. Did you have something to add to that, Nizar, perhaps? No. Okay.
I didn't catch whether this transformation was going to be a stochastic one or from the dialect to the MSA. Because you
Yes.
gave us some examples of
Yes.
the ordering. But
Yes, so the idea is, well, first of all, there's a lexical issue. How do you translate dialect words? And there we have a stochastic model. And secondly, then, there will be some reordering. And there, we still have to see to what extent we'll... I mean, something simple we could do is we could try to do chunking at the dialect side to identify the subject and the verb, and then revert them, and then have a model based on the two unannotated corpora, or the unannotated corpus in the tree bank, to learn how often this transduction the switch should happen. So the answer is yes, it will be stochastic.
then you could choose one of the alternate standardizations based on what parses well.
Yes, or we don't do that and we just let the parser make the choices, yes. Yes.
What is the historical relationship between the dialect and the MSA? Is MSA some sort of an Ur language which has kind of disappeared from the mouths of speakers, but is being preserved?
Mona, do you want to?
So basically, MSA in fact is concocted language. So it was made up in the early 20th century to unify for Arab nationalism. So in fact, the dialects, historically speaking, are closer to what we call classical Arabic. But in order to facilitate communication among the different 22 Arab languages, Arab-speaking countries, they created this language in the early 20th century. And it became the language that people use in formal settings. So it's everybody growing up in the Arab world is bilingual. So we all, in the sense of, if you got an education in the Arab world, you can all read it and write it.
But he was showing words which are different.
So
for instance.
lexical
All right.
choices.
Now, does the MSA word never penetrate back into the dialect? I mean, people are just completely immune from using.
No. I mean, you can think of the MSA as a subset of the dialect in a sense.
There's
So-
also, yeah.
So here's an example perhaps where the word for table in Syrian and MSA is similar.
But you have influences from
No, but I
languages
mean,
as
if a Moroccan just would not be called dead saying Tawila.
No, but he would probably, I don't know to what extent. So,
There's
There's
maybe
always
he
something.
has an
I
idea.
mean, there's the lexical variation that happened in the Arab world is actually a result of, so you have to go back about 1,400 years. So at one point, Arabic, or what is the ancestor of Standard Arabic, was spoken in Arabia mainly. With Islam and the spread of the Muslim empire, Arabic became the official language, or the language of the power, in lingua franca, in all of the parts that became part of the Arab world now, or the Arabized world actually. And in these places had other languages already. So if you look in the Levant, Aramaic or Syriac was the language that was used. Historically, it's related through Proto-Semitic to Arabic, right? So there's some things that stay the same, some things are different. But you go to Egypt, you have Coptic. You go to North Africa, you have Berber. In Iraq, you also have close interaction with Persian. So in this list, for example, you see the Iraqi word for maize comes from Persian. The Iraqi word bazuna comes from Akkadian, historically. So there's lots of...
The last.
the last line.
Okay, I just couldn't. Yes, okay.
Isn't this the word metse too for the
My question was
appetizer?
whether in fact this doesn't get mixed ever. Whether in fact if an Iraqi would never say the MSA word.
Right, so actually, yes. So that's the part where we talked about the code switching. And what happens, because you have these two different forms of language, that people, if they say they're talking in standard, they try to stick to rules from standard as much as possible. And you end up with a situation where actually standard Arabic nowadays is highly marked. So if a person is, if you live in Cairo, let's say, or in Jerusalem, or in any of the main cities, there is an unmarked form of the dialect that is, when you talk, nobody's noticing how you're talking. They listen to what you're saying. Whereas if you came from a village, you speak with a different dialect. And if you start speaking in standard, people notice, oh, he's weird. Why is he speaking in standard? He must be like Muslim Brethren, or he must be from some,
or Arab nationalist
organization. Or some, so it actually becomes very politically marked. And because of that markation, people avoid it. So to some sense, there is a certain language cultures that are being created, and people have to beware of manipulating correctly.
There are a lot of parallels, I think, between this situation and Latin and the Romance languages around the 6th, 7th century or so, when if you were associated with the church or administration, you spoke Latin, and you spoke it as well as possible with a classical model. But if you were local and had no such administrative or church ties, you spoke a form of Gallic Latin or Romanian Latin or Spanish Latin, which was getting progressively further away from the model. And the vocabulary items, even the most common words, began to have different. So caput and testa, for example, words for head, were very different because they were actually different objects, metonymous things. So I see an awful lot of parallels between this and and the situation with medieval Latin as the Romance languages broke away.
Except that they did break away in the case of the Romance languages, whereas in the
Right.
Arab situation for 1400 years, they
Right.
have not broken away. They're still not
There's
written.
always political reactions. I mean, there's always political reactions, and it's not necessarily toward the West. Sometimes it's toward the Turks. Like during the Ottoman Empire, the Turks tried to force, language and culture to kind of fortify that this is Turkish area, and the Arabs were reacting to it. And to actually, since Turks and Arabs are both Muslims, you cannot use religion as a factor of differentiation. So they went to this form of Arab nationalism. Later on, in the 50s, for example, and the 40s of this last century, there were movements also during colonialism to try to support the dialects by different groups. And people there reacted to it as, oh, this is Western colonialism trying to break us, we have to stick together. So there's always political factors that have happened that kind of tied in it that were not present in Europe during, that had like this different evolution in Europe going on.
Yeah, go ahead.
I have a question, more of an observation. The bandwidth of communication, topical bandwidth for Egyptian call home, for example, is very narrow. And the topical bandwidth of the Levantine conversations collected on the Fisher model is probably broader, but still different from what you'll find in the talk show collections, right?
Yes.
Have you found that this makes the translation, the cross-dialect parsing much more difficult? I mean, there seems
Yes,
to be
no,
a
this-
technical non-overlap.
Yes, in addition to the whole differences between the dialect and MSA, there is this domain difference that you get, which is almost built into the sociolinguistics of the dialect use and MSA use, which is a problem which we'll just try to tackle in one way or another. It's probably not completely dissimilar to the problem of parsing spoken English, conversational English, where the domains also differ from the the written varieties available, even if you don't have the language difference.
Even just being able to characterize that would be a useful thing.
Okay.
Yeah, actually, I have an observation on this. So I listened to about half of the test data, just the data, the development data that we got from LBC, to several hours. And they're actually quite different.
Which
from
one?
The Levantine. So the Levantine data and the Egyptian data were quite different because in the case of the Egyptian, people called their family members. So it was much more informal to start with. Whereas in the Levantine data, they were hooked up through like a switchboard style with people they haven't met before. So, and they had a topic that was stated in standard Arabic. So there were lots of code switching going on back and forth. So they were discussing the topic in standard, sometimes giving definitions to or like stating their opinion initially in standard. But then when they were start to know the other person, they only get like 10 minutes, right? They were switching more toward dialect. But there was also dialect switching along the way.
I had a question again going back to the topic of dialectal versus MSA. How is MSA related to the Arabic in the Quran? Is it sort of does it take inspiration from it? Is it exactly the same?
So in principle, the position of like the Arab Academy or academies, there's about 5 of them on Arabic, is that grammar-wise, it's the same as the grammar in the Quran. However, lexically, there's a lot of new words, a lot of actually direct translations, or there are different types of translations that they did to catch up with the times. So in principle, if somebody came through a time machine from 1,000 years ago, they would recognize the grammar, but they would not understand necessarily everything. This is, modern standard Arabic is quite a different dialect from classical, but it's closer syntactically to classical than the dialects that are naturally developed.
So is the Quran available in all the dialects, or would that be considered sacrilege?
No.
Jason?
I also have a question for Nizar. You made this slide, is that right?
Yes.
Yeah. So this looks like the electoral map of the U.S. 2004. And we all know that there's, if you broke it down by county, in this case by morpheme, it might look a little different. And also, if you should any of these words be a combination of red and blue, and should any of them be purple in that you couldn't tell, or you couldn't tell without audio?
That's right. So what happened in this, when I did this exercise, I took the transcript as is from the Wikipedia webpage, and there are lots of cases that would like pass as MSA-like. And I had to make the decision, like, well, you know, just to kind of figure out like what is going on actually, to listen to the actual tape itself, like to the actual audio. So I listened to the audio, and the person sometimes would take a word like, for example, nizam, which that's how you say it in standard Arabic, but then sometimes he said it that way, sometimes he says nizam. And I considered that phonological variation basically, well, one case is standard, the other case is Dalek. However, in the choice that was written for the orthography choice, they look exactly the same. But the orthography choice is an artificial choice. I mean, you know, people sit down and say, we're going to make this look similar. And it's not true that every the sound in standard Arabic became a z sound. In some cases they did, in other cases it became a the sound. I mean, there are lots of variation there too. So I stuck to, you know, displaying it using the orthography that was made, but actually sticking to what was pronounced. So there's a combination of phonological effect. There's lots of morphology changes and also syntactic changes.
The lack of standard orthography for the dialects must be an issue for exploiting unannotated data like blogs, right?
That's right,
Yep.
and that's what the LDC tried to address by basically having multi-level transcriptions. So they have one level that is basically, it's always how you know, this is like what they pick to represent the token, and another level where they represent the phonology of the token, how the token was pronounced.
And in the work we're doing on dialect morphology analysis and generation, we also model explicitly an orthographic tier and a separate phonological tier in order to account for
I think we should
variation.
stop. If you have something important, ask me, but.
Is the MSA tree bank is text and the target is Levantine speech? Is there any way to tease apart the speech versus text and MSA versus dialect issue?
Well, I mean, it's transcribed speech, of course. So you're saying that there are these two differences. One is a dialect versus MSA linguistic issue. The other is the...
Between Wall Street Journal and switchboard data.
Yes. So we have these two differences going on in parallel. And we're concentrating on the linguistic issue, and the team next to us will be dealing with the speech versus written issue. So they'll solve that problem.
Okay, thank you very much. Next comes Mary Harper.
Or I'm going to be in trouble. I can always replay it if it's not loud enough. Yeah, I think that'll be plenty loud enough. Okay. Good. So I'm going to tell you a little bit about what we're planning on doing during the next 6 weeks. And a lot about what we've been doing in preparation for the 6 weeks. Traditionally, the parsing problem has been applied to text, where you basically get a textual sentence in natural language processing. You have a parsing system, and out spits the parse tree, right? And there are standard parsing metrics that assume that the yields of the tree that you that the sentence that you have matches the lexical items that appear in the gold standard tree. Now, when you move to the speech recognition problem, where you basically have an input signal, you go through feature extraction, a speech decoding process, you get a transcription. It's not clear that the word string is going to be the same. And so evaluation in particular becomes something that you really have to concentrate on when you're addressing the notion of parsing speech, because the traditional methodology for evaluation is going to change. To give you a sense for that, I have first a contrast between the ASR output that you get from a state-of-the-art speech recognition system and a human transcript of the same audio. What I've done here is I've identified the deletions in curly braces and the insertions / substitutions in terms of the underlying regions. But you can see there's quite a bit of error there from the human transcription. So you can see there's quite a bit of difference. So this is just one excerpt from the RTO4 data. Now the human transcript, if you were going to parse that, is bad enough, right? I mean, this is a huge thing. There's lots of sentences in there. Notice there's no sentence boundary information at all. And there's a lot of phenomena which sort of get in the way of parsing. You can see, you have I kind of see that you know, perhaps you know, we may need to get. I'm not even giving it to you with the prosody, but I kind of, if you look at the stuff in red, if you delete that, you actually have something that's a lot easier to read. And the phenomena that's there in the red is probably going to be misleading to a state-of-the-art parser based on textual type sources. So the challenge of parsing speech is that there's a mismatch between these two systems you're trying to put together. The ASR system that basically is working on segments that don't have anything to do with linguistic segmentation at all. You're basically breaking up the speech based on pauses that don't necessarily correspond to sentence boundaries. And by and large, they're going to produce long word strings without punctuation. The word strings are going to contain errors, very, very errorful. You're going to have insertions, deletions, and substitutions. And the word strings are going to contain phenomena. So even when you get human transcriptions that the textual parsers aren't going to deal with very well. For example, the filled pauses, the speech repairs, and a variety of other things. The traditional parsers that we have worked with heretofore don't use acoustic cues. They process sentences, not these segments. And it's not even clear that you'd want the parsers to process these segments because the segments really don't provide you with good boundaries to really predict the next word and come up with a good structural representation. And then they have not typically processed inputs with word errors. So you're introducing these errorful strings that these parsers have to cope with. So that's bad enough, but then you go to the reference condition, the human transcription. There's all these extra repetitions and insertions of things like that the parser may not cope with well. So the challenge that we're working with is spontaneous speech. We're going to basically be working with RTO4, the RTO4 conversational telephone speech task. And it's difficult enough for the speech recognizer. You have acoustic challenges that it's got to face, like recognizing word fragments. The language models don't currently model disfluencies adequately. And the segmentation may not actually be quite right for the language models to work well. Recognition output is going to be difficult for humans to read, but it's probably going to be much more difficult for a parser. Parsers have polynomial time complexity in the number of words currently, and parsing conversations sides without segmentation is probably infeasible. So there's going to have to be boundaries obtained somewhere. Sentence boundaries are not provided, and ASR segments are inappropriate. The utterances are different from written text. They're planned on the fly, and there's all those disfluencies and so on. Much of the common language used for organizing dialogues are different from textual sources in that a lot of the language is to organize the dialogue and not so much to structure it in the traditional sense. So there's sort of a meta level that's going on in conversation sides. Speech repairs are also tough for standard parsers, and I'm going to show you some examples. So if we can add some additional information to the word stream, the basic idea is you've got some sort of metadata extraction system in parallel with the speech-to-text system. basically with the notion that you could aid downstream processing to provide sentence boundaries and indicate the structure of disfluencies and so on, so that the parsers can actually cope with this speech much more effectively. Other benefits are, obviously, if you add this kind of information, it's probably going to be easier for people to read these transcripts. And also, there's evidence that metadata of this kind actually can improve the accuracy of an ASR system. And that's work done by Sebastian Coco, I don't know how to say his name, Cocos at ICSI. So, under DARPA ears, there were a number of structural metadata tasks that have been investigated. One is sentence unit detection, so breaking these speech segments into sentence-like units. The reason why SU is used instead of sentences that in dialogue, it's not clear that you're speaking in the kinds of sentences that you would apply, that you would call textual kinds of sentences, and so there's a differentiation there. Filler word detection involves things like filled pauses, and discourse markers, explicit editing terms that can show up in speech repairs. Edit word detection occurs in these speech repairs where you say, I was fortunate, where the edit words are the words that really are supposed to be ignored. People are very good at ignoring those words, and in fact, many times when people transcribe, they really have to force themselves to transcribe those things because we filter them out so effectively. And then the interruption point detection includes is this point where you go from where you hit this point of disfluency, this change point where you're beginning to make a change and move forward. So interruption point occurs between the speech repair and the referendum. Now, in the EARS community, these tasks have been evaluated in terms of reference and speech recognition output, and both of them are kind of interesting. There's some parallelism between them, and by and large, by looking at reference, you can actually just potentially cope with these these kinds of extra grammatical kinds of things that show up in dialogue. And then when you bring the STT in, then you're also dealing with the errorful lexical items. So I'm going to give you an example. This is a transcript from the Wombat data set. It's a data set that I've been working with. It's a dialogue concerning wombats and in the town of Arlee and trying to capture them and send them back to Australia. But they're basically, this is a conversation excerpt. And you can see it's very difficult to read without boundary information, right? So we need to know, when you read it, it takes you a while to sort of figure out what's going on. And actually, sometimes you can be wrong because there's errors that can occur in various, so you can actually come up with a variety of hypotheses. Now, if you listen to the speech, the audio.
So, but how do we get them out? I'd say we set a string of charges that will route them out the back. So the charges start at the front and just explode and blow a little something up. But they're really, really loud. And marsupials have really good ears. So that'll really frighten them.
So you can see, you get a lot from the acoustic signal. In fact, it's without the acoustic signal, I would have an awful hard time making sense of that. Now, if I take it and mark it up with metadata, structural metadata, where I've marked the disfluencies, the referendum in red, I've marked the interruption points and so on, and I've also marked the fillers in the little brackets and so on. You can see that this is much more understandable. Markups really do help a lot. And by and large, these markups might actually be able to be exploited by the parsers as well. And we're going to talk about that. Certainly the parsers would benefit from the sentence boundaries and potentially the sentence boundary types. And it's possible that if you were very good at identifying these disfluent regions, that you could actually pull those out and then have the parser actually parse something that's closer to something that looks more like text. So scoring metadata is something that's in the bag, basically. NIST came up with this metric, and by and large, all of our results are going to be reported using this NIST metric. Basic idea is you have a reference, your gold standard, where you have some notion of where the boundary is. Let's, for the sake of thinking about it, think about it from the perspective of sentence boundary. So the reference has a string of words, and you've got these boundaries. And you have some sort of alignment between the system and the reference words. And basically, you've got two hypothesized boundaries, right? You've missed this one, so you have a deletion. This one doesn't belong there. It's an insertion. And then you've got one that's correct. Based on the NIST metric, basically, you've got 2 errors out of 2 boundaries in the reference, and so you have 100% error. So the metric is high. If you actually used a per boundary metric where you have basically 6 boundaries that you could put a SU boundary or not, then your error rate would be 2 out of 6 or 33%. This in general is the one that's used because you want to basically be able to apply the metric whether you have a perfect one-to-one correspondence between the words or not, and so we use the NIST metric. So the goal of our workshop is to basically, our workshop session is to explore the synergy between metadata and parsing. And with the notion that if you improve the metadata, your parsing accuracy should improve. And hopefully, if you can incorporate more structural information into the metadata systems, that can also help as well. But first, we're going to explore the impact of metadata extraction on parsing speech. Now, there are a number of SU issues that you can think through. Obviously, you could imagine performing supervised training on parsers so that the parser identifies not only the structure, but also the sentence boundaries at the same time. But that becomes quickly infeasible. I mean, due to computational complexity and memory issues and so on, I mean, these conversational slides can become quite long. You're going to have to segment in some way. For edited regions, you could actually perform supervised training on the edited regions as well. I mean, you have a parsed tree bank, and the edited regions are marked, and so you could actually learn, quote unquote, the grammar of edits. So this is computationally tractable, but there are some representational issues with respect to most parsers, or many of the parsers. Many parsers actually cannot represent cross-serial dependencies, and I'll show you why that's important in just a sec. But fortunately, it's a simple matter to pass NBEST metadata hypotheses to a parser, and you could work with those. So speech repairs, and in particular repetitions and content replacements, which are the most common speech repairs, have this cross-serial dependency structure. And you can see that I need a ticket to Boston. There's a correspondence between need and want and the and which helps you to identify the fact that there is a speech repair. So you have a reparandum, an editing term, and a correction where you've got this nice cross-serial dependency. And context-free grammar-based parsers are just not going to deal with that cross-serial dependency. It can't represent it at all. Exceptions of parsers that could deal with it are tree-adjoining grammar parsers or constraint dependency grammar, other kinds of dependency parsers. So what we're interested in doing initially is to take a metadata annotator, in particular the ICSI SRI UW system, and we have speech segments that we get from the ASR system, and we can actually work with transcripts, either ASR or reference transcripts, and feed the speech segments and the transcript into the metadata annotator, and you get a transcript plus metadata. And you can feed that into a genre-trained parser in a variety of different ways. I mean, you can train these parsers in a variety of ways. So you could actually train the parser with the notion of edit. And these can be NBEST. And then in the end, you can control the parser, different kinds of parsers and so on, and get parsed transcripts. And evaluate the impact of metadata quality and reference versus ASR output on the quality of the parsers that you get. And so you want to evaluate it. Now, how do you do the evaluation? Well, this is really tricky. Obviously, you've got word mismatch, but you also have sentence boundary mismatch. So this notion of one-to-one correspondence between the trees is just not there, right? And I'll show you an example in just a minute. There are alignment issues, so you might want to align the reference transcript with the ASR output. The reference transcript is going to be the basis for your gold standard tree, and they need to be aligned in some manner prior to computing some sort of Parseval type score. Now, you can actually work on conversation sides with super trees, right? Now, the parser is going to work on SU by SU by SU, but in terms of evaluation, you can still evaluate the conversation side. And that's the approach that we're taking. Now, there are several metrics you could look at. There's the standard Parseval bracket-based method. There's some dependency-based and leaf ancestor things that were implemented by Brian Rourke, and I just want to show you some of the issues that we have to deal with. So this is an output from a speech-to-text system with metadata markup. So it's hypothesized that there's one sentence, and yet there's three from the perspective of the gold standard. So the three sentences, the alignment of the three sentences are shown by virtue of the colors, right? So you have the black, which is sentence 1, the red, which is sentence 2, and the blue, which is sentence 3. Now, the words are not quite right, but you have this big bracket, right, representing all those three sentences. This is the gold standard, and I didn't even have room to put the third tree, but it was small. But you can see that there are issues in terms of alignment. The words are different, the trees are different, and so on. And so by virtue of basically creating a supernode and hanging them all together, you can actually do these metrics. So we need to compare parses over potentially different yields. The reference syntactic parse for reference words and automatic syntactic parse for ASR output. And some metrics rely on, some of the metrics we were talking about rely on this externally provided alignment. You can't do the Parseval metrics without, and leaf ancestor metrics without. But we also have this head-to-head dependency metric that can actually be evaluated with or without alignment. And so part of what we're going to be doing is evaluating these various metrics over the course of the workshop. And there is a package, a new package, Sparseval, that's speech Parseval, I believe. It's not really sparse, but it supports the use of all these different metrics. And it also allows for some open-closed class sensitive evaluation. Some interesting baselines. So we have using reference words versus speech to text metadata results. So these are the NIST evaluation error metric. You can see for SU boundary, when you go from reference words to speech to text output, the error increases for all of the different types. So SU boundary without type, SU boundary with type, and edit words, the edit word error is quite high. And we take this metadata for the dev2 set, which is one of the sets we're working on, and we actually parse using the notion of where the sentence boundaries are and where the edits are, take them out, and parse using Charniak's parser trained on switchboard, which is actually different enough from the RTO4 notion of what a sentence is. There's sort of a different sense. We actually have a number of results. If we use human annotated metadata and human transcripts, this is using the dependency F measure, so this is without alignment. And I decided to report these metrics because these ones are really harder to get with the alignments. But we have an 84.36% dependency F measure for human-human. If you move down to system-generated metadata, you have a little bit of drop, but you're really actually, I think, losing the most based on the not having the right words. And so you can see that there are some interesting results there about what factors are impacting your ability to work with the data. Now, there's a lot of things that you can do here. to potentially do better. These were just simple baselines using switchboard-trained Charniak parser. And these results are where we train the parser without notion of edits. If you train the parser with a notion of edits, actually the errors are, the F measure drops a little bit. Now, to explore the synergy between syntax and MDE, ultimately what we would like to be able to do, now the metadata system that we have currently doesn't utilize a lot of deep syntactic information. It uses chunking and part-of-speech tagging type information and so on, but it isn't using a lot of information from the parser. And so one of the directions that you might take is, okay, we know that better metadata is going to make better parsing, right? What is the impact of the structure in terms of being able to detect some of these metadata events? And so you would evaluate in terms of the NIST metric by virtue of building a new system. Now, the closest thing we have to a system that gives you a sense for what would work out would be this noisy channel model for detecting speech repairs that was developed by Johnson and Charniak. And basically, they split the problem into a source and a noisy channel portion, where they actually model the noisy channel portion using a tree adjoining grammar so that they can actually pull the stuff that has cross-serial dependencies out. And this is their basic system, where they have the transcript, they have information about the interruption points from the metadata system, and they have this noisy channel model. This is the parser model that's giving them some notion of the syntax of the clean part, the clean portion. They have a maximum entropy re-ranker that uses this information, and they use some filler word detection together with this re-ranker in order to return marked edits and fillers. So what's interesting here is the contrast that is, or the improvement that you get from adding the syntactic information. The stuff in parentheses is from the standard metadata system. So you can see when I work with human transcripts, I get a nice improvement in terms of my ability to detect edit words, filler words, and interruption points.
What are the numbers?
These are the NIST error metrics. So these are the standard metadata metrics, where you've got the total number of errors divided by the total.
High is better or low is better?
High, this is error, right? So low is better.
Low is better.
So you can see you've got a blow up of error as you go from human transcripts to STT, right? And it is interesting. You should realize that this is using the standard, the definition from the ICSI SRI UW system for SU and the probability of an interruption point in the system from the basic metadata. And the edit word detection is provided via re-ranking using the noisy channel model, and the filler words are just simple deterministic words. And the interruption point detection is done by virtue of using edit word detection together with filler word. So anytime you have an edit, you would expect that there was an interruption point. Anytime you have a filler, you've got a similar interruption point by definition. So clearly, syntax helps. And of course, the better the parser, the more tuned the parser is to the language phenomena that we would expect to see, the better it would be. So obviously, accuracy of parse information will help. And it's probably going to help the most with human transcriptions. The question is, can you really help this case a lot? And how negative is the impact of parse errors in terms of metadata extraction? So the resources we have, we obviously have the switchboard Pentry bank, which is not entirely consistent with the RTO4 MDE specification. We have the EARS RTO4 metadata corpus, which is marked up with SUs and edits and so on. And we also have, thanks to our sponsors and LDC, a new RTO4 tree bank. Currently, the dev2 and the eval sets have been completely double-checked and proofed. We're still waiting for a final version of the dev set. But these actually have allowed us to move forward, and in fact, the results I reported earlier were with the Dev 2 set that we got from LDC. Now, we also have been working with various parsers, and at least initially, early on, we've been doing a lot of work with Charniak's parser based on the fact that it was easy to use and it was in the can, basically. The ICSI metadata system is also available to us, together with all these ASR output. And then we have also a variety of other tools to provide features. Oh, I'm sorry. I'm almost done. The RTO4 data that we're using for evaluation is annotated with metadata that has been used in the RT metadata benchmark test. There's the gold standard parses. And you can see how many words there are here is available. We have recognition output, and using all this data allows us to actually evaluate the synergy between parsing and metadata performance effectively. We've constructed, the tree banks are constructed. We've trained parsers on switchboard 3 tree bank under various conditions, with and without edited. We've modified the metadata parser and the metadata system to output NBEST metadata hypotheses, and created a sparse-eval evaluation and used it for baselines. And so all of this is in the can. And obviously, what we want to do is put the pieces together and explore the synergy between these two pieces. And I would like to acknowledge our team, all of whose names are listed. We also have a lot of external people who are quite deeply involved. And then we've gotten assistance from several other people. In particular, I'd like to give mention to Ann Bees and the LDC tree banking team, because they really have come up big to get us something from February or March, early March, when we gave them everything to give us the data sets for now is wonderful. And of course, our sponsors and everyone here at CLSP.
Okay, we have about 5 minutes for discussion.
Yes.
So, am I right in understanding that you're not using any unconventional parsers except maybe for the Johnson and Charniak?
No. I'm working on some unconventional parsers. John's working on unconventional parsers. It's just not enough time to talk about it in 20 minutes.
I see, okay.
So yes, in fact, I think one of the more interesting things is to see if different style parsers do. So Brian is going to be using his parser, for example. John Hales is putting something together as well. I plan on working with CDG as well as Charniak's parser. And I believe that others, there's so much that you can just do with one parser, but we do plan on doing many things with several parsers. So the results you'll hear in the end will involve many parsers.
Right, not all of which are straight context-free
Yes.
parsers.
Yes. And in fact, I think that to me is one of the more interesting things to do. Is, the noisy channel separation is kind of nice, and actually with the small amount of data that may give the best results anyway, right? To be able to separate out those two pieces. But I still have the intuition that if you model those things more tightly, that you would do better. That's my intuition.
A couple of quick questions, both in terms of information. One is that your F measure goes for parsing from about 84% with human annotations and human parsers to, human metadata, to 76 for automatic metadata, to 65 for ASR output.
And this is on the Dev 2 set. The eval set, I think, is a little harder.
Yeah, just as a point of information, this is all Fisher, right? What would Charniak, what would you get on the switchboard part?
On the switchboard part, the dependencies are like 86%. So
the fact that it's Fisher is not a big deal.
And well, there is the problem here is we actually are dealing with the fact that the parser is being trained on slightly different notions of what stuff is, right? So the edit definition's different, and the notion of a sentence is different. There are a lot of longer sentences in switchboard than would ever have shown up in the Fisher set, for example.
It's only 86 to 84.
Yeah. So, but still, I think that those things may actually have some interaction with what we end up doing.
And then I had another question on this. The other question was, you said there was a 55% error rate in identifying interruption points. And of course, that has to do with the fact that if you get a wrong filler word or a wrong edit word where none exists, whatever you hypothesize.
Well, or if you miss one, which is probably more common, right? Especially in the STT case,
Right.
where you're gonna think it's the word instead of right?
Yeah. So is there can you have a conditional number, meaning given that you
Yes.
found the right edit word or given that you found the right filler word? How do you then? What is
Oh,
that?
in terms of the metadata.
Yeah, in terms of how accurate is the interruption point if you get the filler word right and the edit word right?
I don't have that data. I don't have that data.
So maybe the focus should be on the first two and the interruption point is this one.
I think the edit words and the interruption points are really tied, and so if you don't get the interruption point right, in general, you probably aren't going to get the edit words right either. Because so much of what you do in terms of detecting the edit words is based on knowing this is the point where I'm going to have to start looking for cross-serial dependencies. If you take if you take notion of the interruption point out of Charniak's system, he actually loses a lot.
Any other questions? Yes.
Very brief, and you probably told me this before, but the fourth cell that's difficult to evaluate, could you do an alignment? And
Sure, you could do an alignment.
would it be interesting or informative or?
I don't know. I initially had thought so, and I've heard enough people tell me that they didn't think it was, but it actually may be worth taking a look at. It's just a matter of scripting things up properly, and so it would be a reasonable thing. One of the big deliverables, I think, is going to be a best practices strategy for handling evaluation. That I think is going to be a nice outcome of the workshop. Also, a better understanding of the synergy of these pieces.
Okay, thank you very much. Dan, you have a minute?
Sorry about that. I know. I need to go. Sorry.
Yes, that's right. That was up there. Food compensation. Yeah, ultimately it doesn't work very well because then you sort of follow the food code. You need more.
Second after we put it in, so it's recognized that it was.
It worked on Friday. So actually this, I think my laptop may be doing something funny because it's not blanking, even though there's 3 different modes and one of them has a blank here, and that's not happening. I have a floppy disk here, yeah.
I know it's hard, but it's just so huge that this is a work on the complication.
Say again. We could try that. I don't know how to do the display thing, so I don't know how to do this either. I have a port, it's just the mouse port essentially. So where is it that I'm copying it to? What is there, like a device, a removable disk? Okay. Okay. Save. And then I just pull it out. Worked on Friday. I don't know what happened. PowerPoint. Oh, is PowerPoint going to work on Apple? Opening day. Is this mic on? People here? Oh, I see. Okay. How do I scroll? Is it arrow keys? Okay.
You mean the part that was well?
Okay. Hi. I'm Dan Malamed. I'm here to talk about statistical machine translation by parsing. When I had the zany idea last fall to try to put a workshop team together to do this topic, I had no idea who I could get on board. Today I have with me an embarrassment of riches when it comes to talent, literally from around the world. I'm thrilled to be in such company. So I'll tell you a few of the things that we hope to do in the next 6 weeks and beyond. First of all, as most people know, machine translation currently, even though it's getting better all the time, often still produces what we call word salad. And there's a general consensus in the field that just bolting trees onto traditional, or even not so traditional, but finite state-based SMT doesn't seem to help. An additional problem is that translation systems, at least the statistical variety, tend to be very slow. And what's also keeping the field from making progress faster than it is the rising complexity of such systems as systems. So, given all this, why are we interested in translation by parsing? or more generally, syntax-driven approaches to translation. Since this is a language engineering workshop, let me talk about the engineering motivation, although there are maybe other motivations from linguistics and so on. The engineering motivation is that you need fewer parameters to represent interesting aspects of the data if you are serious about syntax. So for example, in a finite state-based system, I might need separate parameters for every French adjective to indicate that it should follow the noun rather than precede the noun the way it does in English. In a syntax-based system, I just need one parameter to represent the fact that adjectival phrases follow their noun heads. If you have fewer parameters and you have finite computational resources, it's nice to know that fewer parameters are, of course, easier to estimate. And what's also important but doesn't get mentioned often enough is that not only will you be able to estimate the syntactic parameters more easily, but in a machine learning setting, all the different kinds of parameters interact and affect each other. So better estimates for one kind of parameter should also help with the other kinds of parameters, like word translation probabilities. So the motivation from engineering is that you should be able to get better accuracy for a fixed amount of training data, and conversely, you should need less training data to get to some fixed level of accuracy. Okay, so suppose we accept this motivation and we want to build a syntax-driven statistical machine translation system. If you really accept this motivation wholeheartedly, then you will want every part of your system to be syntax-driven so that it can get the benefits these benefits from involving syntax. And if you want to do that, then you might build a system that looks, I'm skipping ahead, sorry. Let me first address one possible objection to using syntax that one often hears, which is that, well, isn't involving syntax computationally too expensive? Well, this is a myth, right? The fact is that even though the worst case computational complexity of translation by parsing is polynomial with high exponents, systems that are currently in vogue in the worst case are even worse because they're exponential in the worst case. So this is not really a practical objection. It's actually more of an objection from theory, but even then it's misguided. Now, having said that, of course, we have to remember that if you just try to add syntax on top of the kind of system that is currently used, i.e. a finite state system, then of course you're actually going to incur the cost of both. So that's going to be worse than either one in isolation. So of course we're not going to do that. We're just going to use syntax directly from the start in all parts of the system. And what's interesting to note is that in machine learning, often when you have when you're trying to do machine learning over structured inference, such as trees, you might expect the better models to actually train faster, right? So again, there's this myth that if you want better accuracy, you have to sacrifice computational efficiency or vice versa. This does not necessarily hold. There's hope that you might actually be able to get the best of both worlds. Okay, so if we accept syntax as something we want to use throughout the system, then you might try to build a system that looks something like this. And don't worry about the details, right? My point here is that this is just a complex system, right? There are many pieces. And in case you're curious, blue is for training, green is for application, and yellow is for evaluation. But building systems of this kind and using them in research on statistical machine translation presents several challenges. Such systems are hard to study, right, in a scientific manner. If you want to do controlled experiments, you have lots of things to control. Right? You have many parts of the system you need to worry about. And if you want to do exploratory data analysis, Such a system makes it difficult to assign credit or blame for changes in performance. So much of the improvement is by guesswork rather than being more methodical. More generally, such systems are difficult to modify and extend because, let's face it, most scientists are not good software engineers. When one tries to build a complex system like that, especially given paper deadlines and funding limitations, one inevitably hard codes much of the system, and that makes it difficult to modify and extend. More broadly, such systems are difficult to replicate by people other than the author. Right? So we see numerous papers on machine translation involving syntax these days, but given typical page limitations, it's inevitably the case that not all the details are in the paper, and that makes the system difficult to replicate. Right? So if I want to, if I read a paper about a system and I think to myself, okay, what would happen if I took this system and I tweaked this little piece or put this other feature on top of it? I just can't do that because I don't have the system, right? And I can't build it given everything else I have to do. So that's another limitation of complicated systems. And so all these factors basically mean that the community is slowed down, the research community is slowed down in its research progress in this area. Now, of course, advances are being made. We've seen lots of papers, for example, in this past ACL that make us very optimistic about this approach. But I believe that without these limitations, progress would be much faster than it actually is. So, one of the things we want to do this summer is reduce the complexity of such systems. And to do that, we're going to build on a particular insight about the nature of such systems, which is that if you look at this diagram again with lots of pieces blanked out, it turns out that the core algorithms are actually all the same algorithm. There are a couple others there that are trivial, but the non-trivial ones are all the same algorithm. This insight implies that instead of building 5 complicated components, now you have to build just one, right? You have to debug just one. And then, of course, you reuse that one component with different parameters throughout the system. And what's even more interesting, to me at least, is that this one algorithm is what we call a generalized parser. Now, I'm not going to go into the details here of what that means. Suffice it to say that it's a direct generalization of ordinary parsing algorithms. And that helps us a great deal with our second goal. The fact that this is based on ordinary parsing gives us decades of pre-existing research that we can adopt and generalize instead of reinventing everything from scratch. Right? That's a huge advantage to this approach. So, with the insight that machine translation is so strongly connected to ordinary parsing, we can structure our scientific investigations along the lines that have already been drawn in research on ordinary parsing. So some of the things we might study are the effects of different grammar formalisms, different parsing algorithms, different machine learning techniques. And in each of these categories, we will have plenty to learn from the ordinary parsing literature. Of course, we're also going to do some engineering. This is a language engineering workshop, after all. And so our scientific experimentation will be, the science that we do will be chosen in support of the engineering goals of speed and accuracy in machine translation. And An additional goal is to demonstrate the portability of this approach to different language pairs, the easy portability. So at the very least, we're going to work on 2 language pairs simultaneously. And while we're doing all of this wonderful science and engineering, we hope to simultaneously accomplish a third goal, which is to ensure that such science and engineering can progress unabated in the future. We have some excellent and eager students on our team, and we're going to do our best to get them hooked on this kind of work. Okay. More generally, in addition to our specific research goals, we want to, not only do good research ourselves, we want to enable others to do research in this area more effectively. So those of you who know about the workshop from 1999 know that at that workshop we released a piece of software that had a tremendous impact on the field in the sense that still probably half the papers on machine translation that one reads use derivatives or descendants of this software toolkit. And we want to repeat that success by releasing our own toolkit, which we hope will catalyze this paradigm shift that we're witnessing towards syntax-driven machine translation. So this toolkit will be an end-to-end system for translation by parsing. It's going to involve a relatively simple and yet general architecture that can handle many variations on the theme. It involves an intuitive and flexible object-oriented design. And I mention that simply to differentiate it from other systems where design is probably too strong a word. We'd like to have an efficient implementation with documentation. System's dynamically configurable, easily extendable, and we're going to make it freely downloadable. I probably don't have the time here to go into any of the technical details, but just to give you a little glimpse of what this system looks like. If you know about UML diagrams, this is a snapshot of the software as it currently stands. And I guess I can talk more about that if people are interested, and certainly afterwards. Okay, and we have a larger goal as well, sort of a more programmatic goal. In the late 1990s, and to some extent in the early parts of this decade, although this trend is starting to reverse, but it was a case for a while that machine translation research was sort of devolving into its own subfield, where practitioners didn't actually pay much attention to what was happening in the rest of computational linguistics. I think that's a bad thing, and I would like to see machine translation sort of brought back into the fold. And the strong connection between translation and parsing that we're going to build upon in our workshop, I hope should make both fields pay more attention to each other, because we believe that MT can improve by using parsing, and if that happens, then of course the people who do parsing can claim another application of their ideas. And to me that's a good thing in the long term. So to summarize, these are our 5 goals, some short term, some more long term. And we'll see how far we can get. That's it.
Open for discussion.
So the generalized parser seems to be sort of the core of your proposal, but you refuse to say anything about it.
That's not that I refuse. What would you like me to say?
Could you just say a bit more about it?
Okay, so let me define it. If a parser is an algorithm that takes a string and produces a tree, generalized parser is something that takes a tuple of strings and produces a multi-tree. What's a multi-tree? Think of it as a multi-dimensional tree. If an ordinary parser is based on a ordinary grammar, generalized parser is based on a transduction grammar. What else can I tell you? I mean, I haven't.
How is that different from a synchronous grammar?
In fact, the 2 terms are synonymous. I'll bet transaction grammar came first.
Transaction grammar makes much more clear than the term synchronous. First of all, it's the first term from 68, but it's much more clear what the relationship is between the transducer and the transaction grammar, which is the declarative form of the transducer, abstracting away from which is the input and which is the output. And it's, so it's sort of natural because transaction grammar has transaction rules, ordinary monolingual grammar has production rules. That's the relationship. It's a straight generalization from the monolingual to the bilingual case.
All right. This being taken care of.
I'm going to ask Dan if he has any slides on the state of affairs of the actual research, the corpora, what part of the code is working, and what do you want to accomplish. A little more details on what you're going to do in the next 6 weeks. I know you had these slides at some point. I don't know if you have them right now.
Well, the slides I had at some point were probably what we hoped to do. At that point, nothing much had been done except for part of the prototype. So more specifically, you want to know, sorry, what?
So for example, what's the state of the French-English corpus? What kind of numbers do you get on them right now?
Okay. So in terms of baseline, I'd have to say we're a little behind schedule. One of the effects of having such talented people on the team is that they're extremely busy. So we don't have numbers yet. The corpora, right, so we're working on at least 2 language pairs simultaneously. I think the Arabic-English work is more advanced at this point than the French-English. In fact, why don't I ask Keith what the state of affairs there is, because he knows more than I do at this point. But in terms of corpora or tools?
So we're using the Bickel parser to train on the Arabic tree bank, the Pan-Arabic tree bank. And right now we're able to parse their parallel 10,000 word parallel translations of the Arabic tree bank and build a synchronous grammar from it. But we don't have a baseline for a large amount, trained on a large amount of data at this point.
But you do have the data in place, let's say, from the last NT round.
Yeah.
Whatever, how many 100 million words there are.
Yeah.
Is this a question or?
No, this is a question. I know they were trying to get this all together. I just didn't know whether they had reached it. And I guess you're going to evaluate on the 04 test set, is that correct? The 02 or the 02?
Probably, but I don't know if we actually decided specifically yet.
Okay.
Is the system focusing on context-free grammar, context-free transactive grammar, or are you interested in the system and/or the experiments in looking at other formalisms as well?
We're interested in everything. It's just a question of how much we can get
scope
done.
of the workshop.
Well, I won't, actually. What we're going to do is going to start as simple as possible and then do controlled experiments by adding one little bit of complexity here, one little bit of complexity there, so that we can measure the effects of every little change. And we'll see how far we get.
The simplest case is the inversion transduction grammars.
Absolutely.
From a point of view of the complexity, time complexity. And you're already looking at quite hairy polynomial there in terms of the time complexity.
Well, Dan has assured me that it's not a problem because of pruning.
Okay, I won't touch that yet. To try to go beyond that in terms of the specifics would, obviously be premature as a first step to try to.
In the experiments, I was asking more about the architecture of the software.
Oh, the software, the software is built to accommodate whatever.
You have a picture of the architecture, right? Maybe that's not Jason's question. But he had this big boxology of.
Well, actually, Jason's question pertains more to the later boxology here.
Yeah,
this one, right? So, is there a way to get a pointer on the screen? Okay, let me just point here. So this is an object-oriented design, right? The grammar is an object, right? The only current instantiation is this concrete class, but there will be others, and it doesn't affect the rest. And we'll implement other instantiations as we get to them, right, in terms of our experimentation. Nizar.
Can you say a couple of things about, like, in terms of training, what are the requirements? So if you need, like, parse, you have tree banks on both sides, right, with the aligned text. I'm sure you make use of lots of data without them. Can you say some more?
Yeah. So that's actually very interesting, right? There are scientific questions about what sort of bias from other corpora or what have you is required to make a system sufficiently accurate for some definition of sufficient or sufficiently fast. And this is an experimental variable that we're actually going to play with, right? So the software is built so that you can play with any variant of, monolingual tree banks for all languages involved, or tree banks for just one of them, or for none of them, right? Similarly, for word-to-word models, we have different varieties that we can just plug and play. So this is, we're going to do all the above.
To be more specific, we have, our own results from the past, and also more recently, results from people like Dan Galdeo's group and Herman Nye's group, have been that if you impose those tree structures in advance, that you're going to degrade your performance. It's better to learn to have the tree structures be data-driven. So that's sort of, I think, the most sensible working hypothesis and this is across Chinese English, Japanese English, German English, and I think French English.
Khalil?
So I'm wondering about the issue of efficiency. Don't you need many more strategies like pruning, like approximations, which you don't need in the case of finite state models? For example, the case of latent structure, syntactic structure is in this case latent. So if you want the probability of the sentence, you have to sum over the probabilities of the trees that derive, or derivations that result in the same sentence. And these kind of problems are not solvable polynomially as far as we know. So don't you lose the power of the trees in the process of approximating all the way? I'm wondering.
Well,
isn't there a risk this happening?
So let me answer the first part of your question first. Let me point out that when people do finite state MT, they typically use a stack decoder, something like that, and the stack has a finite limitation on length. So they are doing pruning like crazy. Right? It's not the case that you don't need pruning in the finite state case. Right? On the contrary, you need to prune more heavily in the finite state case because the space of possibilities is exponential instead of polynomial. Right. Now, I guess the second part of your question is, don't you lose something by doing approximation? Well, yes, of course. Right? But we hope that because we have fewer parameters to deal with, if we design things right, that we will need to lose less. Does that answer your question?
But let me add, it's not true in the case, for inversion translation grammars, it's not true that you cannot actually calculate in polynomial time if you want to sum over the probabilities of all the possible derivations for the same translation. I.e. for the same sentence, so you can't. You might not want to because you might still consider it to be too expensive.
I mean, even for context-free grammars, if you have a lattice of sentences and you a lattice of paths, then one and the same sentence can be over multiple paths, say. Even a context-free grammar will give you a...
That's true.
Yeah.
If you have a lot.
Yeah, but you don't have a lattice in the input.
Well, so the other thing that I wanted to mention is that experimentally, it hasn't helped to try to do that. I mean, if you make a Viterbi approximation,
you get something.
You get as much accuracy as you need.
Yeah, I believe so. That's practice. Yeah.
One more question. Okay. Okay, well, thank you. I didn't see you because...
It's okay, I have one. Let's break.
Okay. So we're going to have a break, and next we're going to convene in the lab.
Correct.
You know where the lab is.
Still some juice
And we're going to convene there at 11:25 in our decision.